There is a keyword in the C language called static. We can use the static keyword to give us some more options for the scope of various entities. Let's have a look at that. The entities that I'm referring to are functions and global variables. And you can see in the code here that I'm showing you how you might apply the word static to a global variable and how you might apply it to a function. Now, it is actually possible to apply the static keyword to a local variable, but it means something different if you do, and I'm going to show that to you in a moment. But I'd just like to focus on this first use of the word static here as it applies to global functions and global variables. If you put the word static in there, it has the following effect on the scope of those entities. It restricts the scope. It restricts the scope from the entire program to the current source file. Let's take a global variable for example. It means that if you put static in front of a global variable declaration, then that variable will only be visible within the scope of the current source file. If you were to try and access that global variable from another .c file, you would get a compiler error message saying, I don't know about that variable. And the same applies to functions. If you have a static function, you cannot call that function from a .c file that is different to the one that the function is actually defined in. Okay, so that's what static actually does. Now the question is, why would you ever want to use that? Why would you ever want to impose such restrictions on yourself? Well, I'll answer that question by telling you about something that happened to me back in my early programming days. I was working on a large-scale system that had probably a couple of hundred .c files in it, and I created a global variable. It seemed like the obvious thing to do at the time, and I created it, and it was called count. And then I coded it. It was very simple code, and a little while later, a couple of weeks later, we discovered a bug in the whole system. Now, it didn't seem to have anything to do with this particular code that I'd just written. It was relating to something else entirely. But we eventually found that the problem came down to another global variable off in some other .c file, and that global variable was called count. And that it was interesting that that global variable seemed to be getting changed at odd times. Now, can you see where I'm going with this? What you may or may not know about global variables is that if you have two global variables and they both have the same name, then what you really have is just one global variable. In other words, if you create a global variable called count in one file, and you create another global variable called count in another file, and then you compile and link those two files together, the compiler, or in actual fact the linker, will resolve those two global variables into one global variable. Thus the term global. Global means it applies to the entire program. So you can't have two global variables with the scope of the entire program that have the same name. Just like you can't have two local variables that have the same name in the same function. So I had actually introduced a bug by creating a global variable in my little .c file and then manipulating it. What I was actually doing was manipulating the other global variable, or really they were both the same global variable. And so a piece of code in another part of the system stopped working. Now, the static keyword could be used to clear up this mess. All I would have to do is put the word static on each of the two global variable counts, and then I would suddenly have two global variables, but they would no longer be global, they'd be static. Each one would be visible only within the .c file in which it was declared. Thus they wouldn't interfere with each other. My count, the one that I created, would just be used in my .c file, and the other count would just be used in its .c file, and never the twain shall meet. There would be absolutely no way that if I said right count equals 17, that could mean any other count other than the one in my .c file. In other words, I couldn't accidentally overwrite the one in the other .c file. And that is the point of having static variables, so that you are totally free to call your variables and your functions whatever you want, without fear of accidentally calling them the same as something else in another .c file. So we'll have a look at all of that in just a moment, but first I want to show you the other use of the static keyword. Now you can actually apply static to a local variable, and when I say a local variable, what I'm really talking about is a stack variable or a block variable if you like. In other words, anything that's not a global variable. And when you do, the effect is different. What is that effect? Well, let's have a look. Say for instance we had this local variable called total, and I put static in front of it. What would happen is that every time I called the function accumulate here in this example, the value of the parameter x would be added in to total, and it would be accumulated into the variable called total, which would then grow between each call to the function accumulate. And what does that mean exactly? Well, by placing the word static there in front of the definition of total, I've actually specified that the variable total shall retain its value between calls to the function accumulate. So in other words, let's say you call accumulate once and you pass it in a value of 6. Then after that, total will have a value of 6. Let's say you call accumulate again with a value of 10. Then after the second call to accumulate, the total will have a value of 16. Notice that this total is in fact accumulating, as the name might suggest. Now that's something you cannot normally do with a local variable. Every time you call a function that has a local variable in it, that local variable is reinitialized, or it loses its value and must be reinitialized. So let's now look at a summary of the properties of static local variables. A local static variable retains its value between the calls to the function they're declared in, as we just saw. Now, this represents a change in the lifetime of the variable, but not the visibility. The visibility has not changed. That local variable is still local to that function. No other function can access the variable other than the function it's declared in. But the lifetime of the variable has changed. In fact, the lifetime of the variable has changed such that it is now the same as the lifetime of any global variable or any global static variable. In other words, the entire duration of the program. Now what that means is that local static variables are actually created in the static area of memory at the time that the program begins, and they have a lifetime through the entire program. They are destroyed when the program ends. That's obviously different to just a block variable, which is created when that block is loaded on the stack, and obviously destroyed as soon as the block is taken off the stack. And needless to say that these variables retain their value throughout the entire lifetime, until you manually change it yourself. Now you may have been wondering about the lack of an initialization in that last example that I showed you. Let's go back and have a look at it. Notice that total variable, we're adding things into total, but we've never actually initialized total to anything. So what is total initialized to? Well, like every global variable and every global static variable, local static variables are initialized to 0 at the beginning of the program. That is part of the definition of the C language. It is safe to assume that every static variable you see anywhere in the program, if it doesn't have an explicit initialization, it is implicitly initialized to 0. Now I could explicitly initialize it to something else. I could say static int total equals 4 right there. And what would happen is at the beginning of the program, total would be initialized to 4. Now you might think that every time into the accumulate function the total would get reinitialized to 4, but that doesn't happen. Total would only get initialized to 4 once at the beginning of the program, no matter how much it might look like it's going to happen every time you go into the accumulate program. So we don't need to worry about the initialization of static variables. They're always initialized to 0. Okay, so now we know both of the uses of the word static. One is to restrict the scope of a global variable or a global function, and the other is to increase the lifetime of a local variable. Let's now go and learn the golden rule of scope. Like all golden rules, this is more of a guideline. It's not actually a rule. If it was a rule, then the compiler itself would complain if you violated it. This is just good programming practice. and it is. Variables and functions, and hash defines for that matter, should always be declared with the smallest possible scope. In other words, make all your variables and functions as local as possible, which then of course gives us the corollary: don't use global variables. At least don't use them wherever possible. You've got many other options before you need to employ a global variable. And here's the options that you do have. For variables, you should first try and declare a variable as a block variable, typically a local variable inside a function. Then, if it turns out that the variable needs to retain its value between calls to that function, then you can make it a block static variable. Then, if you find out that other functions in that same .c file need to access the value in that variable, and it's not practicable to pass that variable as a parameter to those other functions, then you would make it a global static variable. In other words, give all the other functions in this .c file visibility on that variable. And then, if it turns out that you need to provide the value in this variable to other functions in other .c files, then and only then would you make it a global variable. But theoretically, you're supposed to not design your program such that that is ever needed. But occasionally it is. For functions, it's somewhat similar, but a little simpler, because there are only two choices. You can restrict the scope of your function to just the current .c file, which is recommended. All functions should be declared static if possible, and then if any other functions outside the current .c file need to call those functions, then and only then do you make them global. And of course, with hash defines, there aren't really that many scope options. You can either create a hash define in a .c file, which means it will only be visible in that .c file, or you can put it in a .h file, where it will be visible to all the .c files that include that .h file. And obviously the preference there is to make it the smallest possible scope first. In other words, put it in the .c file unless another .c file needs to access that same hash define. So what I'm trying to say is, only increase the scope of a variable or a function or a hash define when it is absolutely necessary to. If we go back to my example that when I caused problems by introducing a count variable way back when in my early programming days, both I and the programmer responsible for the other code should have created our global variables as statics. I've actually got an excuse because I didn't know what a static was at that particular point. But my colleague had no such excuse. Anyway, it was a very good way to quickly learn about statics. Hopefully you guys will not make the same mistakes. I've created here a project called static. It contains two files, static1.c and static2.c. Here is static1.c. We've got a global variable called count. We've also got a function called func1. This simply sets count to have a value of 1. That's all it does. In the main, we call func1. We call another function func2, which you'll actually find in static2.c. I'll show you that in a second. And then we print out the value of count. Hopefully func2 will do something to count as well. So func1 will do something to count, func2 will also do something to count, and then we'll print out the value of count. And that's pretty much the entire program. So let's have a look at static2.c. Here it is. Now notice here we also have a global variable called count. Firstly, I just want to address that. Is that a different global variable, or is it the same global variable? Note that I'm going to compile both of these two files together and create one program out of them. Now, I don't expect you to know the answer to this question. Is it 1 or is it 2? So I'll tell you the answer. What the linker does, remember the linking phase of the compilation? What the linker does when it encounters two global variables that have the same name is it combines them and treats them as the same global variable. If they have a different type, if one's an int and one's a float, I believe you get an error message at that particular point. but I'm not sure. You might have to check that. Certainly if they are of the same type, they are combined. So we saw a global variable called count in static1.c, we've got a global variable called count in static2.c, they're both of type int, therefore they are the same variable, they are the same. Okay, so func2 here is going to now add 1 to whatever count was. So let's go back to static1.c. Func1 is setting count to 1, and then func2 from the other program is going to increment it by 1, so the value that it prints out should be 2. Let's check that. Compile, no errors, and run. The value of count is 2. Excellent. So far we haven't really proved anything except that global variables can be accessed from more than one file, and if there's two global variables with the same name and the same type, they are merged into one variable. I'd like to have a look now at the keyword called static. Let's see static2.c one more time. Okay, now what I'm going to do to the global variable here is I'm going to call this static int count. Now what do you think that's going to do? Well, it's going to make sure that this particular version of count is restricted to just this file. There'll be obviously another version of count, which will be the global version of count, which will have a slightly different scope to this one. Theoretically, and only theoretically, it is possible for func2 to have access to the global variable called count, the global variable from the other file called count. But this count, the static version in this file, is kind of getting in the way, if you like. You always remember when it comes to two variables that have the same name, it always takes the one with the smallest scope, and the static int here has the smallest scope. So the count, when func2 is adding 1 to the value of count, it will be adding 1 to this local one, this static one in this file. Now recall that static variables are always initialized to 0, so theoretically it's just going to increment the value of this count by 1. Now recall that the func1 from the other program, this here, it also sets count to be 1. Well, it initializes count at 1. So now if func2 gets called after that, and that adds 1 to count, it won't be adding 1 to this count, it'll be adding 1 to the other count. So this count should still be set to 1, and the other count should be set to 1 as well. So the printf should say that the value of count is 1. So let's compile and see if we actually do get the value of 1. Okay, no errors, and run. The value of count is 1. Excellent. Okay. So what I hope I've proved here is that by setting this particular count to be static, we've effectively hidden it from the other file. The other file has no access to it anymore. In fact, we have now two variables, both called count. One is a global variable, truly global in the sense that it is theoretically accessible from all files, and then we have one that's, if you like, a static global in the sense that it's visible only to one file, but it's visible to every single function in that file. Okay, let's now look at another program I've got. This is a standalone program. This demonstrates the other use of the word static. Remember what that was? Let's go and have a look at it. This is static3.c. Now, I've decided that I want to have a function that works in the following way. I wanted to print out this line of code here. I wanted to print out these words. But I only wanted to print out those words once. No matter how many times I call the function, I wanted to only print out that value once. Now, how would you do that normally if you didn't have, say, a static variable? Well, you might decide to use a global variable and count the number of times that you've called the function func. Now, you could also track that as a local variable inside main. You could say, how many times have I called func, and you could keep a counter of that inside main. But you may actually be calling func, this func, from some other place. You may not be calling it from main, so you'd probably need to have a global variable that you would then set inside func. The variable would be declared up here somewhere, and func would be incrementing that global variable every time it got called. So we would then know inside func whether the function had been called or not, and therefore we could decide whether to print out this message or not. Now that's all fine and that would work. However, we don't need to go to a global variable yet, because we can do this. Well, before I do it, let's actually test this program and see if this is working. You can see what's happening. I initialize the variable to 0, which obviously has to be initialized. Now, if I say if we are not called already, in other words it's the first time, then print out the message, and then set the value to be 1. We have been called. So let's run that as it stands. No errors, run it. Okay, so we call the function 5 times and we get the message 5 times, which is probably what you'd expect. Reason being that this particular variable here, called called already, has a lifetime that lives and dies with this particular function. So when this function finishes and we drop back into main, and then we go back into this function again, this initialization gets called again, and we go through it. So it's reset to 0 every time. Now, even if we didn't have that, that still wouldn't solve the problem, because if we didn't have that, then called already, the variable, would get a random number in it. In other words, it wouldn't be initialized at all, which is not good. So we will definitely have an initialization. So to solve the problem, I can simply do this. Create a local static variable, or a static variable inside a block, a static variable inside a function in this case. Now, this is how it's going to change the program. This line, this assignment statement here, the initialization setting it equal to 0, that happens once and once only. It happens right at the beginning of the program, even before main gets called. It's interesting, and it only happens once. It does not happen at all when you call func. So we come in here, this does not get run, so this gets run first. We first see if called already is 0, and if it is, then we print this out, and then we set called already to 1, and then we drop out of func. Now, when we drop out of func, this variable does not go away. It is static, it stays there. Then we call func again, we come back in here, we do not reinitialize it to 0, we immediately check to see if it is set to 0 or not, and this time it won't be set to 0 because it will have been set to 1 as the very last thing that happened to it. And so hopefully this message will not get printed out at all. No matter how many times we call function, it will only happen once. Let's check that. No errors, and we only get the message once. That's quite handy, that sort of facility to be able to do that. I can think of a good example where that might come in handy. Let's say you have a function, you've got a great big system running, and you've got a function that simply prints out the current date. But you want this function to work anywhere in the world. If it's an American date, then the month will be printed before the date. And if it's an English date, then the date will be printed before the month. You get the idea? So you call this function and you give it a date and just say print out this date. Now, what that function will hopefully have to do is query the operating system to say, well, where are we? Where are we? What is the local way that dates are printed out? Most operating systems offer that kind of information. However, going and accessing that information from the operating system can take time, and you may have to print out lots and lots of dates. You don't want to be going and accessing the information every single time. You only need to do it once. You need to do it once the very first time. So you can see where I'm going with this. You can say, if I haven't been called already, then, for example, go and get the date configuration from the operating system, and then store it here in a static variable. That would increase the efficiency of the program. The program would run faster because it wouldn't have to query the operating system every single time a date needed to be printed out. Okay, so there's a good example of why we might need a static. Okay, so that pretty much concludes this chapter. It's a short chapter. Let's now just have a look at some quick exercises.